In this section, we're going to talk about integrating LISP with non-LISP sites at the same time. So what if we have router 7 and router 6 from our previous examples, and we want to reach internet destinations that are not serviced by the map server and the map resolver? This is where those proxy routers are going to come in order to do a tunneling on behalf of the non-LISP sites in order to connect to LISP. So as we talked about the different roles in the network, we had the ingress and egress tunnel router. Respectively, these are the ones that are asking the map resolver what's the matching between the endpoint ID and the routing locator, or in other words, what's the address of your application and where's that application located? What's the router's link to the WAN? We then had the egress tunnel router that's receiving the traffic from the core, so it's leaving out of the core, it's going into the LISP site. We're decapsulating it, and we're also registering what our mapping is between the endpoint ID and the routing locator. Now, in the case that we want to then reach a non-LISP site, we need another router that's going to proxy this same type of behavior. That the proxy ingress tunnel router is going to connect LISP to non-LISP sites, and the proxy egress is going to do the same thing. Normally, you combine these in the same role, which is the PXTR. Same logic as the XTR, which is what we had in our examples, where we had router 5 both doing the ingressing to the core and then the egressing out of the core. We're going to say we're going to use router 2 here as the proxy XTR, and then that router 10 would basically be the internet. Now, in terms of bidirectional routing, this does assume that someone is going to have to advertise the routing space for the endpoint IDs. So now the address is 6666-7777. We will have to advertise those to the rest of the network. The difference being, though, the core that we're tunneling LISP over will still not need to know those addresses. Okay, so what I mean by this is that router 2 is going to take those two addresses, 6666/32 and 7777/32, and we're going to put a static route that's basically a placeholder. Okay, we're then going to advertise these over to router 10. Let's say we're going to advertise these with BGP. But the core of the network here that we're basically just tunneling LISP over, these guys are still not going to need to know these individual sources or destinations. They will need to have a forward route to exit out of the rest of the network. So for simplicity, I'm simply going to advertise those into ISIS, which is already running in the core. Okay, but this doesn't really relate directly to LISP. This is just normal routing logic. Okay, so on router 2, if we look at the show run interface gig 1.210, I'm going to enable ISIS on this link. So let's say that if we show run interface gig 1.12, okay, we have ISIS process 1. So let's say that we go to gig 1.210, we're enabling ISIS on that. Okay, now from router 1's point of view, if we show IP route for 10.2.10.10, which is this particular address, we should have reachability between these two. Okay, this is assuming that 10 is going to have a route back. Okay, then on router 2, we're going to run BGP. So let's say we have BGP 2. We're going to peer with 10.2.10.10. Let's say they're in AS10. And we're going to do a network advertisement for 6666 and 7777. If we show IP route for these, right now we don't have a forwarding entry installed. So in order to actually originate the BGP route, we know that we have to have at least an exact match in the routing table matching against the network statement. So we're going to do this with a static route to null. So IP route to 6666/32 going to null 0, and same for 7777. So again, this is not directly related to LISP. We're just trying to establish bidirectional routing reachability, that we know how to get to 10, and 10 is going to have to know how to get back to the LISP sites. From router 10's point of view, we're then going to enable BGP and peer with router 2. we show IPBGP summary, we see the peer is up, and we should see in a second that we're going to start to receive those two prefixes. Okay, let's look at router 2 and show IPBGP. We should see in a second it finishes converging, and then these are going to get installed as best paths, and that we can advertise them. Okay, so let's come back to this guy in a minute. Okay, the other thing that needs to be true is that we need to make sure that we have a regular forward path from the LISP sites to the non-LISP network, which in this case, from router 5's point of view, it basically means we need a default route facing towards the core. So on router 5, if we were to look at the show IP route for 10 to 10 to 10, which is this guy here, we don't have a specific match for it, but we do have a default entry. Okay, reason why, if we look at the show run pipe include IP route, we just have a static default. Okay, but we do need to have some sort of forward lookup, because this is going to be not a LISP tunnel destination that we're going to reach. Okay, what this means is that if we were to look at a packet capture here, and let's say that we're going to look at regular pings, let's say ICMP, if we were to go to router 5 and ping 10 to 1010, we'll see that the traffic is going to route all the way to the destination, but the destination can't reply because it doesn't have a reverse route yet back in. Okay, so it's basically right now a one-way traffic flow. If we went to router 10 and look at the debug IP packet or the debug IP ICMP, we should see those messages coming in, but it's not going to know how to reply back to them. Okay, so next let's look at router 2. Did it advertise those routes? Yes, it did. Okay, so now on router 10, let's look at the show IP route. We now have those routes advertised through BGP. Okay, next step we need to do is to tell router 2 to register with the map server and tell the map server that it is going to be a proxy when someone wants to reach the non-LISP aware sites. So essentially what's going to happen is that a packet comes in from router 6, and 6 is trying to reach 10 to 10, 10, okay, which is this guy here. Router 5 says, I don't have a specific entry for this, so I'm going to ask the map server. Map server is going to say, basically, no, I don't have a mapping for that, but I do have a proxy. So what you should do is forward the traffic natively, not LISP encapsulated this direction, and it's going to leave via router 2. When the traffic returns back in, router 2 is going to say, I need to find where the packet is that originally came from. Okay, so it originally came from 6666. From router 2's point of view, now the destination is 6666. We're going to ask the map server. Map server is going to say, yes, I have a mapping. It's going over to router 5. And then this is going to get LISP encapsulated as it returns. So in other words, the traffic flow as it goes outbound is going to be regular IP. As it comes back in, it's going to be regular IP. But then as it goes from 2 to 5, it's going to be in the LISP encap. This again means that the other devices in the core of the network, like router 1 in this case, router 1 does not need to have a route back to the original customer network, which is router 6 here, because it's going to be tunneled over it. As long as we can reach the routing locator, which is router 5's address here, then we should be able to forward the traffic. Okay, so the rest of this configuration is going to go solely on router 2. So what it is going to look like is, first off, the router 2 is going to say it's going to be a proxy ingress and egress tunnel router. So we're going to run the LISP process and say that we're going to be an IPv4 proxy ingress router and proxy egress router. Proxy ETR, proxy ITR. Okay, for the ingress traffic, which is going to be the ones that are coming from us and then going into the LISP network, we need to know where is it specifically going to go to. So we need to ask the map resolver, what's the destination that you know about? What are the particular routing locators? So we say who is the map resolver for the proxy, or excuse me, who is the source of the proxy ITR? That's going to be us here, local. The ITR map resolver is going to be router 8. Okay, 8's the one that knows about the database. Okay, we then need to say for router 2, well, what do you specifically want to ask them about? Because you don't want to ask the map server about everything, because if we're on the border between the LISP site and the internet, there could be hundreds of thousands of destinations literally that we're trying to reach, and we don't constantly want to be pounding the map server saying, do you know 1234, do you know 1235, etc. So instead what we're going to do is limit what request do we want to ask. We do this by statically setting the map cache. So we're going to do a map cache and say that we want to resolve 6666/32, and we're going to send a request for this. Okay, so we don't know where it's located, but we want to ask about it. Same is going to be true with 7777. So anytime a packet is going to either of those, we should ask the map resolver. Okay, so if we show run section LISP, we're the proxy ITR and ETR, and then we're going to ask the map resolver, do you know where the routing locators are for either of these guys? Okay, now let's take a look at it from the end-to-end traffic flow. So if we go to router 5, let's go ahead and now, or not router 5, router 6. So we're going to ping to 10 to 1010. Is that the right address? 10 to 1010. And the source is our loopback. Okay, if we look at this now in the data plane, so let's just send one packet out, and we see it going 4 hops there and 4 hops back. So if we look at this from the diagram, these hops should be from 6 to 5, from 5 to 1, from 1 to 2, and then from 2 to 10. Okay, that's 4 on the outbound path. Then likewise, another 4 back on the inbound path, 10 to 2, 2 to 1, 1 to 5, and then 5 to the destination. Okay, we should see that the first of these packets was a native IP encapsulation. Okay, so this is just the ping. Okay, then the next one is the one that is going from 5 out to 1. This is getting encapsulated as what? ICMP over IP over Ethernet, or in other words, it's not tunneled. Okay, it's just normal native IP traffic. The key about this is that the transport network in the middle does know how to reach this destination. The transport network doesn't know how to reach the source, but we don't yet care about that because we're not routing the traffic based on the source address, we're routing it based on the destination. So the traffic is going to leave, the problem is going to come in when the traffic tries to return. So we should see that on hops 1, 2, 3, and 4, this is just regular IP over Ethernet. Okay, once it goes to return, this is router 10 sending the echo response. It now gets to router 2, which is the second hop. Router 2 is the one that now puts it in the LISP encap. And it's saying to get back to the EID, we're going to send it towards router 5. It then goes over the next hop, which is going to router 1. We're still tunneling it to 5. It gets to 5. 5 is going to decapsulate it and then send it as native IP back to the final destination. So in a real design with LISP, basically where this guy would be located is at your internet exchange point. So wherever the service provider is peering with other providers and you're going from an internal LISP network to the non-LISP internet or whatever your non-LISP peers are, that's where you would want that tunnel to start. Because the key is here that in our internal network, which is this in the core, this is non-LISP aware, so we need to tunnel the traffic over it. That's what this guy is doing by saying we're going to proxy as the ETR and the ITR on behalf of this guy, but only for the return traffic. because the outbound route we already know simply based on our default. But when the traffic is returning, since one, XR2, XR1, etc., doesn't know how to get back to this guy, then we're just going to tunnel it to this destination. Okay, there's a couple questions here. One is, does traceroute work in this context? I believe it is not going to work. So let's see from 6, if we were to trace to 10.2, 10.10, source of 6666, we should see that the intermediate hops are going to be broken, but once it goes all the way to 10, then the return ICMP unreachable is going to be LISP encapsulated, so it's going to work on the way back. So notice here we saw routers 5. We lost the packet at 1. We knew about it at 2 because 2 knew how to LISP return it. And then 10 was able to return it because it was returning it as regular native IP because the BGP route was being advertised in this direction. So it goes kind of against normal routing logic because if we look at router 2 and look at what it has installed in the table, these LISP destinations, it's null routing. But the null route is basically a placeholder saying it's not really being null routed. We're going to ask the LISP encap and figure out what's the routing locator that we're going to tunnel the traffic towards. And as long as we know how to reach the 10.155, then we're good to go. But this, of course, is based on the fact that we knew what destinations do we want to ask about. Otherwise, if we asked about every single destination, that's going to be inefficient from the control plane point of view. Okay, there's a question here. Aren't all unknown destinations when hitting the XTR sent to the proxy TR by the map server and the map resolver? No, only in the reverse direction for the ones that you request. Okay, so let's actually look at the full control plane exchange in the capture, and then we'll see exactly what it is specifically doing. So let's say on router 5, we're going to clear IP LISP map cache. And actually, let's say this on all of these boxes. And let's look at this first from a LISP to LISP site. So we're going to go from 6 to 7 and see what the resolution is. Okay, so in the case of our capture, we're going to look at just the LISP control plane. Okay, on router 4 and router 5, we're going to look at the show IP LISP map cache. Right now, we don't have any entries. Okay, now router 6 goes to send a packet. We're going to ping 7777. We're going to ask just once. Okay, if we look now at the capture, let's look at this step-by-step of what specifically happened. Okay, first things first, router 4 says to router 5, is your routing locator still there? Okay, this is actually unrelated to the map request and the map resolution. This is 4 and 5 pinging each other to make sure that both of the edge routers are reachable. Okay, it's a default behavior. It's like a high availability feature. Okay, what we want to look for is router 4 trying to figure out how do I get to 7. Okay, so we're trying to get to 7, but we don't know where it is. So what we're really going to do is we're going to ask the map resolver. Okay, so the packet is going to 8. It's LISP control. Okay, 8 is going to get it, and it's going to say that I'm going to send the packet to 3, because 3 is the one that knows how to get to 7. So what happened to start was the data plane packet came in this direction. 5 says to 8, do you know 7777/32? Okay, 8 says, yes, I know this. It sends it on to 3. 3 now gets the packet, and it says, well, I don't know how to get back to 6, which is where the packet was originally coming from. So 3 says, okay, I'm going to tell 4 that I know how to get there. Specifically inside this payload, it's going to tell it what is the destination that you're trying to reach. Okay, it says if you want to go to 7777, you're going to use one of these routing locators. You're going to use either both of my interfaces. Okay, that was this one here, the map reply. Okay, so now 3 is saying back to 4, or excuse me, yeah, actually it went to 4, because the packet went in, actually this direction. Okay, it went to 4, 4 asked 8, 8 passed it to 3, 3 replies to 4. So basically the map server is like a proxy in the middle. It's the same type of logic as DMVPN and HRP resolution. You ask the hub, and then the hub passes it to the spoke, tells the spoke, hey, you do the spoke-to-spoke resolution to cut down on the control plane in the middle. Because the potential bottleneck for this type of design is this guy in the middle that everyone is constantly hitting over and over. Okay, now 4 knows how to get to 3, and then we would see after this, once the map reply is done, then we would do the encapsulation in the normal data plane. Okay, now let's look at for the non-LISP site. So now router 6 is going to ping 10 to 1010. So that's one of the internet destinations. Okay, we see that 4 goes to send the map request. It's asking 8. Okay, it's asking 8, do you know how to reach 10 to 1010? 8 is going to reply. Okay, so let me graph this out. It's first sending, the packet came this way. 4, send it to 8. 8 is going to reply and say, no, I don't know how to reach it. This is going to be a negative reply. Okay, negative reply is forward native, saying there's not a match in my cache. You need to forward this through your regular IP routing protocol. It's not a LISP destination. Okay, router 4 eventually realizes this once the request goes back to it. And okay, so this is the control plane. Now the data plane actually goes to flow. Okay, so the data plane goes in that direction based on whatever the normal native routing is. Okay, now the traffic comes back the other direction, and router 2 is going to ask, how do I get back to the original source? So there should be a message in here that's coming from 2 that is, and I may need to, I think I didn't clear the cache on 2. It's kind of hard to read this because it's showing the inner and outer destinations separately. So what I need to say, let's say IP source is equal to 2222. That's where it should be coming from. Okay, on router 2, let's look at the debug LISP control plane all. And actually, I didn't send that from the correct source is what the problem was. Source should be 6666. Okay, here's now the map request. So the packet is coming back to 2. 2 asks 8, do you know how to get to 6? So this was number 1911 in the capture. So after the packet goes from 2 to 8, so basically the data plane was forwarded, now it comes back in. From a control plane point of view, 2 asks 8, how do I get back to 6? 8 should then reply and say, you need to ask 5. So 8 forwards it to 5, okay, someone that is authoritative for that particular endpoint ID. 5 is then going to reply to 2, so it's kind of a weird crisscross of where the messages are actually going. But we should see here 5 is going to reply directly to 2, and it's telling 2, hey, if you want to reach 6666, you really need to use one of my routing locators, which are either router 1 or excuse me, router 5 or router 4's interfaces. But the key here is that if let's say we hit a random destination where router 6 says to ping 1234. Okay, we're looking at just the LISP control plane. This is the main optimization that you would have to do in a real design. That if I'm asking the map resolver and the map resolver says no, I want to make sure that I don't have to ask the proxy resolver as well because it would be basically trying to resolve every possible internet destination, which is like millions and millions of destinations. So again, the way that we did that was on router 2 to say only try to request these particular addresses, because we know that those are part of the LISP network. So the potential shortcoming of this, deploying it in a real production design, is that there's a lot of manual work that has to go into it. That just like DNS, it's a very static configuration. That you have to know what these potential resolutions are, what are the sources of where your traffic is coming from, what are the routing locators that they're going to potentially exit out of, and then any time that you change that, you would have to correlate between the ingress-egress tunnel routers to the map server config, especially if you don't control the map server. So if you as a customer are buying Lisp transit from someone, then the configuration that goes here that is saying what can you register or what can you not register is going to be dependent on the map server actually configuring it. So if you configured this wrong, like if we said 6667, then whatever that source address would not be able to tunnel the traffic over Lisp. There's a question, so there is an overhead request for all unknown destinations. Yes, there is. You can tell the egress and ingress tunnel router what not to request for, though. The default behavior is that they request for everything, because you're trying to keep it kind of pseudo-dynamic, that you don't really know what is or is not Lisp is encapsulated. And the way that the map resolver is dealing with that is by replying back with that negative reply, is basically saying you need to forward it as native, which was, I don't know exactly where it was in here. It was 8's reply back to 5 or to 4, saying this one here, forward natively. So it means I don't have a route to that particular destination in the cache. You need to do just normal IP forwarding. There's a question, can an ITR and ETR be combined with a proxy ingress and egress tunnel router? Technically, you could run the function all on one box. So they made it modular to begin with, that if you want to distribute the load between multiple systems, you can do it that way. But there's no limitation of saying that I'm not going to be the ingress tunnel router, egress tunnel router, proxy ingress, proxy egress, map server, and map resolver all at the same time. It's just you would constantly be pointing back to your own loopback address, which if you already have a route to the WAN directly, so let's say that like you are the service provider and you're controlling your own internet exchange points, then there's nothing wrong with saying that this guy is basically doing everything. It's just that, you know, if the control plane starts to get overloaded, then you might want to separate it into multiple physical boxes. But keep in mind the difference here between the proxy XTR versus the map server map resolver. This guy is just in the control plane. So it's just responding to requests saying, yes, I know a mapping between the RLOC and the EID. The proxy XTR, this guy actually is in the data plane. So this guy here, this could be like a virtual machine. This would have to be some, you know, beefy box like ASR9K, something like that, that's going to actually do the forwarding in hardware.